The next speaker, Dr. Mirko Rennert, gained initial experience with biopolymers in R&D projects for film applications and packaging at Polykum Extrusion GmbH. At the Institute for Circular Economy of Biopolymers at Hof University of Applied Sciences, which he co-founded, he was involved in various scientific projects with biopolymers, including as head of a research group dealing with the use of biogenic byproducts. He will show us in his lecture how the stabilization and coloring of biopolymers, biogenic byproducts, can be controlled. Your company's name gives us a glimpse how you process biopolymers, right? By the use of twin screw process. Welcome, Dr. Mirko Rennert from Twin Screw with the lecture Stabilization and Coloring of Biopolymers with Biogenic Byproducts.
Good morning to the audience live here, and good afternoon to my friends in Australia. I'm happy to be here to show you our understanding of the nature and how we at Twin Screw try to make biopolymers more stable against degradation and also more colorful for different applications. Whenever you think about a bioplastic, you can follow this easy formula, right? That the bioplastic is actually always a mixture of at least one biopolymer together with additives. At the moment, a lot of people claim single material systems because they can be homogeneous, recycled, bring back to circularity. Okay, with PET bottles, this might work. But for a lot of other applications, it's not sufficient to have just one polymer and no other additives, right? And when we take a look into nature, how Mother Earth is doing that, she also does not use single material systems. Yeah? Just take a look on this piece of wood, right? We have the cellulose, which is the structure-giving material in this composition. We have also hemicellulose and lignin, who gives the hardness, stability, toughness, right? And we have tannin and lignin, who act as antioxidants and help the tree to resist to, for example, UV. So, and that's exactly the way you can also today construct biopolymer products, right? We need a material for plasticizing, for giving the main mechanical properties. We need other impact toughener, for example, modifier, and we also need additives to help to resist to degradation, like antioxidants. So, but maybe one step back. Let's just think we want to produce this cosmetic cup, and we want to use these polybutylene succinate, right? One basic difference, generally, to the conventional polymers is the existence of oxygen, for example, in the molecule, right? And these groups, oxygen is very electronegative. And whenever you have these combination, these molecules, you will always have permanent dipoles. And wherever you have permanent dipoles, the party is always going on, right? Polyethylene is chemically inert. It's not interested in interacting in so much. That's why you can extrude it at very high temperature and nothing will happen. When you do that with biopolymers, you have a problem, right? And this is mainly driven to these dipoles. Now, when we bring these products to the environment, we have a lot of degradation mechanism, right? Like we have UV light, we have all the time oxygen, we have moisture around us, water, and we have a lot of steps where heat is applied to the product. So this is stress for the polymer. And usually it starts with, here in the PBS, with a hydrogen abstraction next to the ester group, with the creation of a free radical. And then the oxygen say thanks, and it starts to oxidize, right? And this needs to be prevented. Yeah, because the result would be, at first, the breakage of the molecules, then we have the first microcracks, and finally, a failure of the whole product. So this needs to be prevented. That's why we need additives. Right? There's a whole bunch of additives. All of you know that, right? There's a very long list, and today I'm just concentrating on the antioxidation, stability, and on colorants for sure. Okay, what are the antioxidants doing? They can act as scavenger, right? So they stopped already oxidized processes. They can help to heal already damaged molecule part, right? And they can also prevent oxidation. So very nice. This is the same I always say to my students. It's like eating fruits all the day helps also to reduce the free radicals in our body and keeps you healthy, right? And the same is like what happens with the biopolymers. Okay, a big focus of today is the pigments, the colorization, because people do not accept just easy-looking products, so that's why we want to have maybe a unique products like these yellow cups or a blue cup or what else. Okay, and I want to show you today what you can do with bio-based pigments. How does the reality look like today? All of you know that still today, even the total amount is a bit increasing. Less than 1% of all the polymers is bio-based, especially in the field of technical application. And with the additives, the situation is not much better. There are some plasticizers based on bio-based products, but basically still the majority of the additives is fossil-based. And whenever we speak about that, you know, a lot of climate scientists always claim and say, just we want to let you know that we have turning points in this world, right? You know, and we are talking a lot about that at the moment. But we might also not forget that there are other turning points in with respect to chemistry, right? And you see here the current situation with respect to chemical pollution, with the loss of biodiversity, right? This year I'm happy because I have more flue on the front glass of my car, and that's why I hope still more insects are at least in Germany this year, right? So this is something that I'm happy again. But nevertheless, we have a problem with critical additives. For sure, most of them come from fertilizer and so on. But we, as the polymer engineers, we have the responsibility to take care of what we put into our polymers that might maybe degrade in the soil and then lead to some damage, right? And you all know these critical images of a turtle in the sea with the foil in the mouth, right? And this is very emotional. But the soil in this world is, as far as I know from research, polluted approximately 20 times higher than the water, right? And this is our fundamental to grow plants there. And also recently I found out that the first PFAS could be found in the leaves of a tree, right? So they already go their way from the soil into the tree, into the plants, and finally in our food, right? And this is a thought I don't want to extend so much because I think it's quite critical, right? Okay, and something else that happened in 2020 was this paper where these scientists collected several polymers from the market, conventional polymers, biopolymers, and they completely decomposed it. And at the end of the day, they concluded that it doesn't matter if bio-based or conventional plastic, they all have toxic components. They are all the same toxic, right? And you can imagine what happened, shit storm the next day. The media was writing bioplastics are the same toxic as conventional plastic, blah, blah, blah. What they didn't mention so much in detail is that the additives they found in the biopolymers are probably almost the same like they are used in the conventional plastic, right? And this is also something that we should think about because when you today buy a polymer from the market, a biopolymer, it is sometimes already pre-stabilized with conventional additives, right? And this is something we want to change. One of our crazy ideas, and for sure this is quite ideological, is like that, like this walnut, right? The walnut shell is the natural package of one nut, right? And when we cut it, we crush it, we produce a fine powder, we produce a master batch or a compound, and we can now produce a package of film for a lot of hazelnuts, right? Not just for one. And because our idea is that what cannot be bad to a single nut cannot be bad to a whole bunch of nuts, or basically, for example, to the soil, right? So the idea is that, because I think it's very hard to investigate all this interaction of chemicals, soils, all this crazy chemical stuff that's going on. But in my idea, when the nature calculates that a walnut can fall down from a tree to the soil and can degrade and has less impact on the soil health, it probably has also no negative impact when we produce, for example, a box out of it. Somehow this box maybe goes to Australia, I don't know why, maybe for the dirty socks of the athletes at the Olympic Games, I don't know. And whenever we have then degradation there, right, we hope that this degradation has not that negative impact on the soil there. So that's the basic idea. And There's also, I think, we need to educate more the society, the people, to understand, because a lot of people say, I don't want to have degradable polymers. Today, I think we will hear another lectures about degradation. But at the end of the day, also, the nature has almost non-degradable materials, right? There's wood outside there who can become thousands of years or older, even if there's UV, water, moisture all the time, right? It is resistant. And here's one easy example how you can try to construct your biopolymer just by the carbon-nitrogen ratio, right? We have like fresh cut grass can decompose very fast. And for example, wood, which has a much higher relation of carbon to nitrogen, degrades much slower, right? And this is also the way you can design your biopolymers. We try to focus and collect biogenic byproducts. We started on a small scale with the first ideas we had, and we found out that there is already waste streams, right? When I sometimes call my partner and say, come on, I need a new example of a byproduct, do you have? And he says, yeah, okay, the truck is always on the way to you. And I say, hey, come on, I'm happy with a bag, not with a truck, right? But what I want to say is, I'm very convinced that we can also guarantee the scaling, right? That we once are able to show that it is working, that we can scale it up. Here you see the relative amount of the byproducts that are generated through their lifetime, right? And especially with coffee and tea, which are the most consumed beverages in the world, right? We do all this effort from the farm to the brewing just for 3% of the extracts we get out of the product, right? The rest is more or less byproduct. And the same a little bit with all the other stuff. Interestingly, the world is today throwing away or seeing it as a waste what is the most potential biofunctional ingredients, like they are in the peels, they are in the seeds, they are in the pomace, right? The same with the corn and with the tree. I'm speaking about especially the polyphenols, right? Which helps the product to be resistant against UV and all the other degradation mechanisms. And I say, okay, thanks, let's take it. And what we do, for sure, we need to try to investigate the biofunctionality. One easy way is to produce or to make assays just to find out what is the total polyphenol content, right? And here I did that with some coffee samples. Okay, what's the processing way? It's a little bit comparable to what Ulu is doing. I mean, we are not a biorefinery. We try to pre-treat the biogenic byproducts to make them ready to use as stabilizers and pigments, right? So that means logistic is the first step for sure to guarantee that we have a homogeneous waste streams. We have approximately around 50 reliable waste streams that we can continuously get, make them stable, make them storable, and then use as stabilizers. We have to pre-treat them. That means some of them are very red at the beginning. So that means we need to get out the moisture, otherwise we have mold growth and the decomposition naturally. We need to fine grind it. This is one of the most critical points, because you can guess we want to have a homogeneous dispersion of these additives in the biopolymer. We don't want to have weak points for bad mechanical properties, and we don't want to have also not too small particles that can be electrically charged and then lead to agglomerates in the polymer and things like that. So these are the first steps that we do. With extraction, I don't mean that we try to keep it simple, okay? We know there is usually not just one stabilizer in the byproduct. Stabilizers stabilize also stabilizers, right? This is also what the PVC industry is doing, but also Mother Earth is doing that. When I say extraction, we try to take out ingredients that are not sufficient for the final biopolymer product, like water, like fatty acids, and like sugar. Right? At the moment, sugar is one of my biggest problems because when we eat our flambé, whatever at home, right? We want to have it, but in the polymer, in the extrusion process, we don't want to have the Maillard reaction, right? Because you can guess what happens. It will become brown at the end of the day due to the sugar. That's why we need to get it out. Also, chemical modifications are possible. We also play a little bit with that, like coating of our pigments, for example, to make them more thermal stable. This is also something that we do. The important step for us is the compounding. So we bring it already together with a biopolymer, and then it goes to injection molder, film producers, whatever. And also these films were some samples reproduced. So as I said, the fine grinding is one of the most important process in that, and we are happy that we finally found a a process where we have both. We have drying and the fine grinding at once. It works with a turbo rotor, and so we have this air intake, then we add our byproduct, and we can control by the speed of the rotor, right, the turning, and also the way how fine we get the powder at the end of the process. So that's the way we have it. Now they are storable, and we can work with them for stabilization. What we actually are doing at the moment is we don't have hundreds of tons on stock. We are just a small company. We are 4 employees at the moment. We try to prepare them on demand. Okay, we ask the customer which kind of mechanical properties do you need? What are how long will you use it? What are the potential degradation processes that can happen? Do you need fast degradation, slow, whatever? And do you need stabilizers or colors, right? For sure, we also need to guarantee that it's really working. Here, what you see is a standard DSC curve of a PHBV, right? And the brown curve, as you see, is without the additive. And what you see is this exothermic peak above 250 degrees Celsius, and this is associated with oxidation, with oxidating degradation processes. This big endothermic peak can be traced back to thermal degradation. Unfortunately, we are not so successful at the moment to extend that to higher temperatures, but for most of the application, it's okay. And what you see that whenever you add here, for example, a coffee byproduct, 3, 4, 5% is already working. We completely can stop these oxidative degradation processes, right? What we else found out that, because at the beginning I was a little bit disappointed when we made the assays and tried to find out how much polyphenols are into our byproduct, that the values were quite low. And then we found out that where the byproducts with the low values have a high content of dietary fibers. Right? And finally, with the help of research and our own experiments, we found out that most of the antioxidants are insoluble bound into the dietary fiber. But whenever you have the condition in the extruder, high pressure, temperature, they can be released from the dietary fiber. And this is more or less a very good match, because this is exactly the point where most of the interaction of the biopolymer takes place, right? So it's a perfect match, that the release of the antioxidants and helping to scavenge oxidized molecules in the biopolymer chain, for example. So perfect match. Yeah, we also, for sure, we also tried to test the UV stability. Here you see an example of a thermoplastic starch film, 50 micron, that we produce by ourselves, right? And we do some weathering tests, right? And what you can see that the first cracks on the native TPS we could see at approximately 200 hours, and with the help of our byproducts, we were able to increase it up to 800 hours. Maybe also not very, very big steps, but the first steps into direction to make it also resistant to UV degradation. Okay, let's talk about the colors. Now, this was the part of the stabilizers. What I was trying to show here, I'm sorry that I don't have New Zealand in that, but I guess the deviation is probably the same, is the natural deviation of the colors in nature, right? For sure, the majority is green. Yeah, it comes from chlorophyll. It has a sense, because from an energy point of view, it makes sense that the world is green. And it's also the most relaxing color for our eye. Yeah? Just think about all the trees, all the grass would be violet. Our eyes would become crazy. We would become crazy, right? And this is simply physics at the end of the day. All right? So you see the deviation in nature. But when you take a look on the deviation of all the colors in plastic products worldwide, we see that, white is the dominating color. Why? Because it stands for hygiene, cleanliness, right? But the question is, do we have so much white pigments? You know, titanium dioxide is also a big discussion at the moment, right? Calcium carbonate and so on, things like that. I will show you the advantages and disadvantages on some later colors, right? But what I want to say is, I know we might not be too ideological at that point, but what is a problem to try to copy a little bit the deviation of the colors in nature, also to the polymer products that we design, right? When we think about the natural color pigments, right, there are different ways to say they are natural, because they can be metal-based. Metals are naturally in our world, on every planet, right? So you can take them like aluminium, right, to bring a shiny silver gloss into your polymer. For sure, we have a lot of natural inorganic pigments out there. I already said titanium dioxide, calcium carbonate, and things like that. The big disadvantage of them, they usually have very high densities. Okay, the target is not to add too much to the polymer product, right? But whenever you need to do that, you increase the density and totally the mass of that. The other problem is healthy risk. There are more and more studies that show that a lot of these color pigments can have negative impacts. I mean, we remember the time when we used plumbum-based pigments, right? Fortunately, this time is over, but more and more studies shows that also other natural metal or inorganic pigments can have a risk for our health. The price is low, right? This is a standard process for the polymer producers today. Add so much calcium carbonate to the polyolefins as you can because you reduce the price, right? Okay, this is the way it's working right now. We focus on pure plant-based pigments. We also can, with a partner, we try to connect these plant-based pigments to some metals to become more thermal stable, for sure, you can guess. The problem is the prices are higher because it's an additional complex process, but the thermal stability is high, density is medium, and the health risks are quite low. And we concentrate on fully biological pigments. The advantages, the price is low to medium, healthy risk is low to medium, density is medium, and also the only critical issue is the thermal stability. You can guess, I already told you, whenever you have sugars, reduced sugars into the byproduct, it can be a problem. And I will show you on the next page why it is a problem. Nevertheless, we, at the moment, actually we want to produce compounds in master batch to provide it to the biopolymer industry, right? But we found out that it could be fruitful to produce our also own products. So we have a small injection molding machine, just to investigate the processability, flowability, and things like that. And the first used injection mold machine that we bought also contained a tool which already had the shape of these golf tees. So we said, okay, why not producing golf tees? You get a lot of golf tees out of 1 kilogram, which is quite helpful for a startup like we are, right? And as you see, we also try to bring a lot of colors into that, because the funny fact is, at the beginning, we wanted to act ideologically and say to the golf courses, hey, you cut your grass every day, give it to me, I produce golf tees out of your byproducts. But then the golfers said, no, but when the golf tee looks like the grass, I cannot see it when I hit the ball and the golf tee is flowing away. So I'm searching all the time the golf tee. So please make it in a contrast color so that I can find it on the golf course. Okay. So we take a look and we finally found some very nice byproducts of spices, and we could also now make them also in a yellow or an orange to help the golfer to find their golf tees. Because here the plan is not to make them starch-based, who will be away after the first rain, but we also use PHAs, for example, to say, okay, whenever it stays in the ground, it will be degraded one day with not so much negative impacts, but whenever you can use it multiple times, do it. So we also add some impact modifier, also based on PHAs, so that the golfer are happy with the golf tees, and we can take higher prices. Okay, I told you that we at the moment, some headache is the sugars, right? And as you can see here, we are investigating the color change independence of the temperature, right? And yeah, Maillard reactions also take place at room temperature, but for sure at higher temperatures, they are accelerated. And finally, you see there's a point when degradation goes on, and finally also the byproducts can become black. So this is for sure something we want to prevent. But when you, for example, take a look on the algae in the middle, maybe it's not so clear here on the screen, that we found out that there's some byproducts who change the color 3 or 4 times independence of the temperature. And I had a nice discussion with Green for Nature in the break to say, okay, it's not necessary to see everything negatively, see it positively. Use it as a sensor for applications who want to have a color change at a certain temperature, right? So and this is maybe the way we should really think about it, not to say I exclude it, no, I take it and maybe I find the right application. Yeah, that's the way we do. We have a compounder here in Halle, and we take several biopolymers. We almost actually tested everything that we could get with our partners, and so this is the general list of colors that we can provide at the moment. Very special are the yellow, pink, and red. That's why I do not add here the name of the byproduct. You know, it's a little bit our idea, and the rest is a lot of time was flowing in to find out what works and also continuously work and reliable. And so that's why this is the current list I want to present to you. Yeah, and with that, I'm more or less ready with my presentation. I hope I could inspire you a little bit that we should not see biogenic waste as waste. We should see it as feedstock for new products. Mother Earth is putting a lot of energy in polymerizing these molecules, and let's take them and produce nice products. So that's why. Thanks for listening. Thanks to my team at TwinScrew. Thanks to Icebeer, who's watching. I've worked a lot with them. And so, yeah, let's have a nice day, and I'm happy to have some questions from you. Thanks.
Yeah, thank you very much. Very interesting thing. I think here are a lot of questions out of the audience, yes? Anybody voluntary to start first? And please come over here. And yes, please, and pick up the microphone.
When we are talking about the use of renewable resources, one of the buzzwords is cascading use. And I like very much your approach to get out the valuable compounds out of the biomass, but you release the sugars. And we from the biotech sector, we love sugars, our microbes like sugars. Do you have any idea how to combine your technology and the remaining sugars? Do you have already any ideas for valorizing, or what type of sugars? I mean, from the different types of byproducts, I can imagine not all of them are already the simple sugars. Maybe it's also some polymers or oligomers. Could you please comment on this?
Very, very good question. As you said, thinking in cascades is also, we don't want to be competitors for secondary food, right? Because this should be even higher from the priority than using them from materials, right? So this is also a topic that we need to discuss. You are right. At the moment, you try to keep it easy. What we try is a wild fermentation, right? To get at least out of the sugars, but not in a very good way to use the sugars for another processes. So whenever you have an idea, you are welcome. Let's discuss in the break to really make it even more sufficient to take the sugar and use it for biopolymers, for example.
Okay, let's talk about this.
Hey, thank you for the great talk. I just had a question, with the certification and biodegradation of biopolymers. As you know, some of the rules are that you're allowed to have 1% of non-biodegradable ingredients in a biopolymer and a total of 5%, so individual component 1%. And I think that's a problem because then some companies, they get away with putting 1% of non-biodegradable additives and so on. Do you think that's a problem? Do you think we should change the regulation? Is that a challenge for your business as well?
Generally, when we today have the first discussion with the customer, he says, I want to have TDS, SDS, and for sure all the certifications. And I say, can we start with first trials and then talk about certifications, right? So basically, this is a claim today that's quite hard for startups, right, today. I understand that totally, and we need to make these certifications, no question. On the other side, yeah, you are right. We have a lot of regulations that I'm not okay with. Right. Also in the conventional polymers, like that a polymer can be called a single material when the heterogeneous components are less than 5% and things like that. So this is also something I don't agree with, right? Yeah, but you are right. I think we need to work closer with also the politicians, with all the people who are writing these regulations, with the science, basically talking about being more transparent. Maybe you have seen we try to be very transparent also with the kind of byproducts. We're talking about that patents, IP is important for sure, but when we are not transparent enough, then we sometimes have these black boxes sometimes, and this can then maybe lead to these regulations that make us problems again. So. Thank you. Thank you.
Thank you. I think there'll be other questions popping up in the breaks, and people approach you there, I'm pretty sure.
You.
Thank you.
Thank you.